Hello and welcome. These are the solutions to Activity 11. Activity 11 is mostly over Chapter 9, a little bit of Chapter 8 as well. It is our last activity before midterm 3, and it's a 2-week activity. So you won't complete this activity in your next recitation, but rather over 2 recitations leading into midterm 3. First question deals with lattice energies and how they're determined experimentally. This is kind of a tricky Hess's law problem. There's a few different ways we can get into it. One is, I think, if you just start thinking of the reactions that kind of go from taking an element like calcium to a gas, and then taking like calcium gas to calcium plus an electron, calcium gas plus losing another electron to the 2 plus ion plus an electron. We're ultimately trying to find, let's make one other connection, is that we're trying to find the lattice energy of CaCl2. And the lattice energy is the energy specifically for this reaction. CaCl2 as a solid forming calcium 2 plus gas plus 2Cl minus gas. So just separating this compound into its gaseous ions. And so the delta H of this reaction, this is the lattice energy. The delta H or E of this reaction is our lattice energy. And so, like, if we can think of what it is we want to do, we want to somehow have a series of reactions that we sum up together where we get calcium 2 plus on the product side. Well, I got that already. And I got to get Cl2 or Cl minus, two of them on the product side as well. Well, let's start with Cl2 gas. Now, the reason why I might start here is just this is the elemental form of calcium. This is the elemental form of chlorine. So we're starting with our elements, trying to understand why they might form these charged ions. And so if we break this apart to 2 chlorine atoms, we're going to want to know that delta H. And then we'll take the 2 chlorine gases and absorb these electrons given up by calcium. And now the key is kind of, well, do we know what the delta H is of these different reactions? Like the delta HF of the gas minus 0 delta HF. Delta HF of calcium solid is 0. So the delta H of this reaction is the delta HF of calcium gas. The delta HF of calcium gas is 179.3 kJs. I'm going to give these all in kJs, not kJs per mole. So we're going to think about the kJs per mole as we go along. 1 mole calcium plus. So 1 mole times 179.3 kJs per mole is 179.3 kJs. Ionizing 1 mole of calcium, that's the IE1 of calcium. So the IE1, 590.0 kJs per mole. I'm ionizing 1 mole, so just multiplying this by 1 mole and doing a second mole, so the delta H of the second step is the 1145 kJs, and again, there's 1 mole. That's where our mole's going. I don't want to have to write this every time, though. Clutter it. 2 chlorine atoms. Now, this reaction here can either be the bond strength of Cl2, so we could do like a bond enthalpy chart. Most bond enthalpy charts list the bond enthalpy of chlorine-chlorine bond of 242 kJs, or we can just do 2 times the delta HF of chlorine gas. So that times 2 is 241.4, right? 243.4 kJs. So I'm just multiplying the delta HF by 2 moles. And then 2 chlorines absorbing an electron affinity of chlorine, minus 349 times 2. That's minus 750, minus 748 kJs. Only thing here that's negative. Now, there's one last thing I need to do. I need to somehow get rid of my elements, or I need to relate the element energies to calcium chloride solid. And this will help me cancel out my calcium solid, my Cl2 gas. And this reaction here would just be the delta HF of this on the reactant side. So 0 minus the delta HF of calcium chloride, CaCl2. So the delta HF of calcium solid and Cl2 as a gas are 0. And that's key here. So 0 plus 0 minus the negative of the delta HF. So that's 7. So it's going to be plus 759.8 kJs. So notice I flipped the formation reaction of calcium chloride. So I flipped the reaction, hence I'm taking the negative of the delta HF of calcium chloride. Okay, so now I'm adding all these reactions up here. And notice how everything cancels. My electrons canceled here. Calcium gas cancels. Calcium plus cancels. 2 chlorine atoms cancel. The only thing that's not canceling is CaCl2, solid, goes to Ca2 plus 2 chloride minus gas. So I do 179.3 plus 590 plus 1145 plus 243.4 minus 748 and then plus 759.8. So I get 2170. Closest to 2167. Maybe I put something down wrong. Why is it not exact? It's not that big of a deal. I'll just do this one more time. 179.3 plus 590 plus 1145 plus 243.4 minus 748 plus 759.8. Yeah. So I get plus 2169.5. Closest number here is 2167. So this is how we take a series of values that are experimentally determined to solve for our desired lattice energy. So it's just a big, gory Hess's law problem. Question 2, dipole moment of HBr is 0.82 debye, bond length is 1.41 angstrom. Calculate the charge of bromine in this molecule in units of electronic charge. So we're given electronegativities here, 2.1 and 2.8 respectively. You would also generally be given on the test that 1 debye is equal to 3.34 times 10 to the minus 30 coulomb meters. And then you'd also generally be given the charge of one electron is 1.602 times 10 to the minus 19 coulombs. There is like a sheet that I think is in the recitation page, my daily quiz page, that has this information on it. This generally would be the only information given. This information here, I don't know, like if you really need the electronegativities, but if you just remember, hydrogen's electronegativity is particularly low, so it's generally going to be lower than all the other atoms it might bond with on the nonmetal side of the periodic table. This helps us know the relative electronegativity difference, that when I'm looking at zero formal charges, that bromine being more electronegative picks up the partial negative. Hydrogen keeps the partial positive. So the electronic charge on bromine should be the partial negative charge, not the partial positive charge. And then I just have to account for mu is equal to Q times R, solving for Q being mu over R. I just have to account for units. And so when I take my mu here, that my dipole moment is 0.82 debye, I use 1 debye, 3.34 times 10 to the minus 30 coulomb meters, and divide this by the bond length in meters. So that'd be 1.41 times 10 to the minus 10 meters. That's 1 angstrom, 10 to the minus 10 meters. I don't think this is usually given. You have to kind of know that. So this 1.41 times 10 to the minus 10 meters. Pretty easy conversion. But we do this, and we get that it's 0.82 times 3.34 e to the minus 30 divided by 1.41 e to the 10 negative. That's 1.94 times 10 to the minus 20. That's coulombs. Okay, now if this were plus one minus one, it'd be plus one electron minus one electron. So we use the charge of one electron. So in electron charge units, the charge would be equal to 1.94 times 10 to the minus 20 coulombs, and I just use the charge of one electron, 1.602 times 10 to the minus 19 coulombs per electron. So it's 0.12. So this is a fraction of an electron. This is our partial charge. So somewhere between 0 and minus 1 for bromine, it's minus 0.12. So for answer D. Which ion below contains an atom with a plus 3 formal charge in its Lewis structure that satisfies the octet rule for all atoms. So ClO3 minus, so that would be 7 plus 6, 6 times 3 plus 1, so that's 28 electrons, not 26 electrons. And so that's a lone pair on chlorine. So this is all the atoms satisfying the octet rule. That has a 1, 2, 3, 4, 5. This is a plus 2 formal charge. BrO4 minus. We're not making double bonds here because we are not expanding past the octet rule based on the thing where it says that satisfies the octet rule for all atoms. So we can't expand our octets here for these Lewis structures based on what's told to us in the question. So bromine should have 7 electrons surrounding it, only has 4. 7 minus 4 is plus 3. And so BrO4 minus looks like it's probably the answer to the question. But let's roll out the others. PO4 would be this structure here. Satisfies the octet rule. Let's do one quick thing for BrO4 minus that we forgot to do. 7 plus 4 times 6 plus 1 is 24 plus 8, which is 32 electrons. And we've used 32 electrons, so no lone pairs for bromine. PO4, 3 minus, very similar. We have 5 plus 24 plus 3, so that's also 32 electrons. So we're good with this structure here, no double bonds, satisfying the octet rule. But now phosphorus has 5 electrons. To give it a neutral charge, it's only surrounded by 4. This is a plus 1. And if we go to PO3, 3 minus, we just have 3 O's. Now PO3, 3 minus 5 plus 18 plus 3 is 26 electrons. So here we have 24 electrons. So we have 2 electrons left over to go on phosphorus. This actually has a 0 formal charge. So only bromate, or perbromate, I'm sorry, has the 3 plus formal charge. Question 4. In its Lewis or resonance structures that satisfy the octet rule, what is the best description of the bond order of the sulfur-oxygen bonds? So 6 times 4 is 24 electrons. So for stopping at the octet rule, that would be getting to this structure and making this one double bond. And we satisfy the octet rule. Now we have the possibility of this or this as well. So we have 6 electrons in our pi system, but we on average have 1, 2, 3, 4 bonding pairs of electrons spread across those 3 SO bonds. These are about 4/3 bond order. So 5, which of the resonance, consider the resonance effect in carbonate, which statement is true. So carbonate is where we have this Lewis structure here. And then the other 2 Lewis structures being this one and this one. So we have again 6 electrons in the pi system, but all the bonds are the same length of about 4/3 order. So all 3 bonds in carbonate are equal in bond length. We don't have one shorter than the other two. So a linear geometry will come up for an atom that has only two domains. So like CO2 has two domains, and HCN would have two domains, also be perfectly 180 degrees. CS2, like CO2, so for CS2, also would have two double bonds. It also has 16 electrons, just like CO2. O3, though, has that lone pair. It has a lone pair because we have 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So you have 18 electrons. This is going to kick this bond into being bent within the trigonal planar electron domain geometry. And then N3 minus is this choice here. So N3 minus is having three nitrogens bonded together. If you start by rule, come up with this structure here. So N3 minus would have 5 times 3 plus 1, 16 total electrons. So that's the right number of electrons, but big charge. Let's make a double bond. Let's make another double bond. Let's reduce this to plus, minus, minus. And then let's call it a day because, like you could do perhaps N triple bond N 2 minus, but that's making this charge higher, so that doesn't seem to be good. And so this is our best Lewis structure for N3 minus. Azide ion is what this is called. And again, one domain, two domains, no other lone pairs, so this is going to be 180 degrees and also linear. So both B and C here have linear molecular geometries. Whenever you have three atoms, the question is it bent or is it linear? O3 is bent. The other two molecules here are linear. Based on Vesper theory, what is the bond angle for 7? Well, we got two domains. That equals linear, equals 180 degrees. Angle 8 looks like 1, 2, 3, 4. So this atom here is tetrahedral. That's 109.5 degree bond angles. 0.5 degrees, not degree bond angles. So 8 is going to be close to 109.5, 7 closest to 180. Let me also notice here, let me also point out here, 8 looks 90, but that's just in our flat Lewis structure. The real structure is going to look something like this. So our real structure looks more like this. So the three-dimensional shape doesn't necessarily take on the two-dimensional shape we sketched that Lewis structure with. Which molecule has a trigonal pyramidal geometry? So trigonal pyramidal geometry is where we get something like, say, for ammonia, it's like we were tetrahedral in our domain, but we had one pair of electrons. So one of the lone pairs takes a spot in tetrahedral, and then we get this triangle that's in a pyramid. So the trigonal pyramid shape is something like for ammonia. Now it's going to arise when we have three things attached. So CO2 is linear. SF2 again, like three bonds is either linear or bent, not something like trigonal pyramidal. Having four things doesn't make sense either. Like SF4, it's going to be a question: is it tetrahedral or is it going to be like seesaw or is it going to be like square planar or something within the larger um, molecular geometries, like 4, 5, or 6 domains. And then, so the only two possibilities are ClO3 and ClF3. So let's look at ClO3 first. So that would be 7 plus 18 plus 1, 26 electrons. This seems perfect because I have the three O's using 24 electrons, and then I get that lone pair I need to kick into this geometry. So ClO3 is perfect for the trigonal pyramidal geometry. Now, if you start to make double bonds, it doesn't really change the picture. Like if you're saying, well, how do I know to stay with single bonds? Does the geometry change if we start to go from this 2 plus charge down to the 0 charge with two double bonds? The answer is I still have one, two, three, four domains. Either way, four domains equals TD electron domain geometry. One of the lone pairs takes the spot of the tetrahedral, and the remaining shape is trigonal pyramidal. So the shape of the molecule, you usually call like the geometry of the atoms, is the molecular geometry name. The shape of all of the electron domains takes the electron domain geometry name of tetrahedral, and then the tetrahedral shape depends on all those domains, and so too does the other shape. So the two names depend on each other, but the name, like you're giving this name based on the atoms. Sometimes we call it an atom geometry or a bond geometry. So ClF3 minus would be the right answer. Now, why not ClF3? Well, ClF3 has 28 electrons, and it's going to kick. And we did this not too long ago somewhere. I think in the extra lecture video from chapter 8, I did this Lewis structure. We ended up with this one here. That's 24 electrons. The 4 electrons left over go on to chlorine. So we have 1, 2, and then 3, 4, 5. We have 5 domains. This is going to be trigonal pyramidal geometry, and it's actually going to be a T-shape molecular geometry, not trigonal. What is the electron domain geometries of BRF5, electron domain and molecular geometry name BRF5? So this is 7 times 6, that's 42 electrons. So bromine to 5 fluorines, that's 8 each. So that's 40 electrons there, 2 electrons left over onto the central atom. Okay, so this is going to be bromine up and down. Imagine this like square wedge coming out at us, and you get this pyramid shape here. And then you get a lone pair on one of the faces that's doing the up face. And so you get a square pyramid downward for the bond geometry. So the molecular geometry name is square pyramidal. And then the molecular geometry name is octahedral. Octahedral because we get 8 sides to our shape that emerge from this perfect shape if you imagine the octahedral shape. You could have called square pyramidal to be square bipyramidal. Like octahedral's name could have been square bipyramidal because it's like a bipyramidal square shape, kind of like how trigonal bipyramidal. In fact, on the previous page, I think I wrote SF, whatever it was. ClF3 actually has the trigonal bipyramidal molecular geometry name, not just trigonal pyramidal. So trigonal bipyramidal. We could have called this name square bipyramidal instead, but the name octahedral, I think, has stuck as a more common name. So octahedral domain, all 6 domains included, and then just the shape of the atoms. We look at the shape left behind and say, well, it looks like a square pyramid. Consider the molecular polarities of the below substances, which, if any, are nonpolar. So SF2, so SF2 is 6 plus 14, so that's 20 electrons. This is going to be bent because we have 16 electrons tied up between the F's, and then 2 lone pairs here. So this is just like water. This is going to be bent, so this is going to be polar. SF4 looks like sulfur, so 6 plus 28 is 34 electrons. So this is going to be sulfur, fluorine, 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 fluorine. That's 40 electrons. Excuse me, that's 8 times 4, that's 32 electrons, and the 2 left over go on to sulfur. And so this is going to take the trigonal bipyramidal shape, and then the atom geometry is going to be seesaw. But the key for this structure here is that it's kind of like the shape for it's kind of like how like water and other things, we get this partial positive charge here, partial negative charge. This partial positive on sulfur is encountered with the nuclei. So the nuclei can interact more strongly with each other. The electrons really, they're so small, so electrons don't really get in the way of another molecule of SF6 parking right on top and having the negative fluorines on another molecule attracted to this partial positive charge on sulfur. So you get this built-in plus minus attraction for two adjacent molecules in SF4. So this would be polar, just like the polar molecule for SF2. SF6, though, ends up being perfectly octahedral. So you end up with the perfect octahedral shape for SF6. All these fluorines oppose each other, negative charge on all the ends of the molecule. Look for one end of the molecule to differ in charge, and that just doesn't happen for SF6. So this is the example of something that would be nonpolar, just like CO2. Same charge on both ends of the molecule. SF6, same charge on all the ends of the molecule. We don't get the exact same minus charge like for SF4. We need like SF5. We need like a fluorine in place of that electron pair, which just isn't there. So SF6 would be nonpolar. PF3 would be nonpolar, or excuse me, this is going to be polar. This is 5 plus 21, 26 electrons. So this is trigonal pyramidal. Because we have this electron pair in phosphorus. The key is with the Lewis structure, you have to be able to see that you get these two lone pairs so that this kicks us into having a partial positive, partial minus. The charges aren't counteropposing each other, so this is going to be something that's polar. And then PF5 is something that is perfectly nonpolar. PF5, 5 plus 35 for 40 electrons. So having 8 per F, same negative charge on all the sides of the molecule. So notice every side of your molecule. So if you have your geometry is linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, if you have those geometries with the exact same atom in every spot, then the molecule has to be nonpolar, just because you have the same charge on all the ends of the molecule. So perfectly nonpolar for 5. So 3 and 5 here, nonpolar. All the others are polar. How many double and triple bonds does this molecule have? So how do we come up with the Lewis structure here? We'll just follow. So what I would do is just, we'll start with CH2 and start with the CH and a C and a C and an H. Now you might not know when you write up versus down, but I kind of, might be alluding to where this is going to be. Like if I want 4 bonds per carbon, I got to do a double here, and then I have 1, 2, 3, 4 for this carbon, and I already have 1, 2, 3, 4 for the next. And then this carbon here only has 2 bonds. So what about this? So that gives it 4 bonds, gives the next carbon 4 bonds as well. And so that would be the structure for CH2, CH, CH. So 1 double, 1 triple. Essential atom below is sp3 hybridized. Well, sp3 hybridization is anything that's tetrahedral. Okay, and so we have linear. This is sp hybridization, meaning that the central carbon hybridizes an s and then a p orbital to kind of do this. Make one orbital here, one orbital here. Now oxygen can pair up with one of them, make a sigma bond, and the other oxygen pairs with the other, makes a sigma. And then we have leftover p orbitals. So here's one of them on carbon, and then here's the other one that's left over. And so we can take orbitals on oxygen and pair them up to make the pi bond in one way, and then we can take the oxygen the other way, make another pi orbital. So CO2 ends up with 2 pi bonds using these pi orbitals, but this is really a long-winded explanation for sp hybridization in CO2 and some implication of that. PCl5, having 5 things attached, is like you have to have 4 things or fewer to be sp3, sp2, or sp. So this can't be any of those 2 hybridizations. CCl4, this is definitely a tetrahedral molecule, 4 single bonds, and so that definitely becomes sp3 hybridized. And so this is just kind of picturing having the 4 chlorines being tetrahedral. BeCl2, that's going to be kind of like CO2 just without the pi bonds. So BeCl, Cl single bonds, no electron pairs in beryllium. And BCl boron trichloride is trigonal planar. So this is going to be sp2. So sp2 hybridization is the hybridization of trigonal planar molecules. BeCl2 is going to be sp hybridized like CO2 is. So tetrahedral sp3 for CCl4. 13, which bond angle is greater according to Vesper theory or the Vesper model. So ammonia versus um, that methane. So methane CH4 has to be a perfect tetrahedral shape. So these bond angles are exactly 109.5 degrees. And then in ammonia, the issue with ammonia is that it turns out to not be perfectly 109.5 degrees, which you would expect for a tetrahedral type shape. But these electron pairs are closer to the nuclei of N, so making them kind of like bigger, and then making this bond pair longer and more spread out. So the electrons here being negatively charged closer to the nucleus repel the bonding pair electrons more, so the bonds get closer together and are slightly less than 109.5 degrees. It turns out it's about 107 degrees in ammonia. So the CH4 bond angle is bigger in ammonia than it is in the CH bond angle in CH4 is bigger than those angles in NH3. PH3 versus BH3. BH3 is trigonal planar, sp2. So these are going to be perfectly 120. The pH in pH3 is going to be closer to 109.5 and even less than 109.5. So pH3 less than 109.5. So the greater angle is going to be that in pH3. And then if we have a double bond, we have two more electrons that can repel the single bond. So the single bonds get closer together than the double bonds. So double bond repulsion, more electron pairs push those single bonds together. So the HCH angle is going to be less than 120 degrees, and the OCH angle is going to be greater than 120 degrees. So the HCO angle is going to be greater, the BH angle is going to be greater, and then the CH4 angle is going to be bigger. How many total sigma and pi electrons do we have here? And so a single bond is a sigma. The triple bond is a sigma plus 2 pi. Now why? Well, you get the sp hybrid orbitals, so you get the sigma, and then you get the pi orbitals overlapping. So that's one of the pi's, and the other one's sticking out of the page. Hard to see. I'm going to get rid of it actually so it's not too confusing, but that's our 2 pi bonds. So we get a sigma, and then again, the triple here is a sigma plus 2 pi, sigma plus a sigma plus 2 pi. So you get the sigma overlap and you get the p orbital overlap. One of them and then the other. So we have a total of 8 pi electrons, excuse me, not 8, 2, 4, 6 pi electrons, and then 1, 2, 3, 4, 5, 6 sigma. Which molecule has the longest CC bond? So we have ethane, ethene, ethine. You don't have to know the names, but like you have triple bond here. That's going to be the shortest. Double in the middle, the longest bond for C2H6. MO theory, according to MO theory, so the order here is our two s orbitals for our atoms and their two p orbitals. And this is for B2C2N2 and their ions. O2F2 neon 2 and their ions over here. So again, the 2s and the two p's overlapping with each other. And the issue here is that the s orbitals overlap kind of one up, one down, and then the p orbitals for an atom. So if you're thinking the p orbitals um, here in energy, in terms of a picture, you have the s, and then you have the p orbitals here. Let's forget about the one out of plane first for a minute. Just think you have head-on orbitals, and you have the other atom, like say in O2, you have the other atom approaching with its orbitals. The orbitals can't really change, flip around, or they got to be centered around their nuclei. So we get our sigma overlap, and then we get our pi overlap. And then the pi overlap not shown is the extra one sticking out of the page, which is also a pi. So you get two pi's, so these are our pi, two p's, this is our pi, two p. And you get just like an orbital switch. In one case, the the sigma 2p is higher than the pi 2p. In the other case, the sigma 2p is lower in energy. We go sigma 2s, sigma star 2s for O2, F2, neon 2, then sigma 2p, then pi 2p, then pi star 2p, then sigma star 2p. Here, pi star 2p, sigma star 2p, and then sigma 2s, sigma star 2s. According to their MO diagrams, which molecule below is paramagnetic and hence would be drawn into a magnetic field? Well, the answer is O2 because that's kind of why we're learning about MO theories. Learn that O2 actually has unpaired electrons. So if we're filling O2 into this diagram here, we're filling in 12 valence electrons into our valence diagram. So we're just going, switch colors. Let me go 2, 4, 6, 8, 10. Notice when I try to apply Hund's rule, and I got 2 more to go, so I apply Hund's rule and I spin pair those electrons and use 2 different orbitals. So I have 2 unpaired electrons, which should pull O2 into a magnetic field. And, if you're just looking at the Lewis structure, I don't think you would predict. You'd be like, well, aren't these electrons spin paired? And usually they are. It's kind of weird in O2 that they're not. There's some like weird structures that people sometimes write for O2 being kind of like this. And it's just kind of like like you like pair some of these, you maybe pair these, and then these are not paired in the same direction. So you get these electrons paired in the same direction. Really hard to picture Lewis structure. I'm sketching what a Lewis structure might look like for O2 that makes sense in its MO diagram. But the MO diagram shows sort of unequivocally that O2 should have unpaired electrons and then making it drawn into a magnetic field. And if you do this for like N2, you'd be putting 10 electrons in here into the side for N2. So 2, 4, 6, 8, 10. I didn't really do that right. So 2, 4, and then it should be 6, and then 8 paired up, and then 10. All the electrons are spin paired though. In nitrogen, C2 would only be 8 electrons, so we'd kick 2 electrons out here, so that's still spin paired. And then F2, 14 electrons, so I put 2 more in, they spin pair those 2 unpaired in O2. So F2 would have 0 unpaired as well. So only O2 of these choices has unpaired electrons. Another MO question. We give you these base diagrams on exams, so it's all about filling in their electrons and understanding what to do from there. Using their bond orders as determined from the MO diagram, arrange the bond lengths of the following molecules. So rank them in increasing order: O2, B2, N2. Let's start with B2. So let's start with B2 over here. So boron has 3 times 2, 6 valence electrons. So we're plugging in for our 2s or 2p. You can think about it being a 2s, 2p, 2s2, 2p1 configuration. Just picturing 2 boron atoms over here, B2 in the middle. So for 2, 4, 6. So B2, like O2, you'd predict to be paramagnetic, but our bond order, the net bond here is just these 2 electrons. So we'd have a single bond. If we want to sketch a Lewis structure, probably something like this, and then these just happen to be paired into the same direction. And so a single bond. So the way we calculate the bond order of B2 would be take the number of bonding electrons. So these 2 plus those 2. So 4 bonding electrons minus the anti-bonding star electrons that went up, and then times a half. So single bond for B2. And then O2, we did that earlier. So O2 would be 2, 4, 6, 8, 10, 12. And so our sigmas, our stars are these orbitals here. So my bond order is going to be 8 bonding electrons and then minus the 4 anti-bonding electrons times a half. Just from the idea that a double bond has 4 bonding electrons. And so half that would be 2. So the bond order of 2 is the pairs of electrons. So we're counting how many bonding electron pairs there are. The answer is 2 for O2. And then if we do this for N2, we're just putting 10 electrons in here. So B2 to N2, We're just putting in 8 and then 10. So we end up at a triple bond for N2. So we have 8 bonding electrons minus 2 anti-bondings times a half. So that's the triple bond, which makes sense for N2. And overall double makes sense for O2. So N2 is going to be shorter, or N2 is going to be the shortest because it's a triple. O2 is the double in the middle. B2 is going to be the longest. Let's actually do one more comparison. Like if you want to compare, like say B2 to F2. So we said, well, what if we threw F2 into here? How would it rank? Well, F2 is single, but the fluorine is small, so F2 would have a bond order of 1. So if we're comparing B2 and F2, we then think, well, which atom is smaller, B or F? And size decreases towards F. So wherever the bond type's the same, 2 single bonds, you would say F2 is definitely going to be shorter than B2. And then, so if we're fitting it into this trend here, that it's going to go N2 less than O2 less than F2 being single, so triple double single, and then B2 being even longer because the boron's bigger. So when we're comparing bonds that are both single, you then compare the atomic size differences. So if you're comparing like O2 and C2, so O2 and C2 are both doubles. They both have bond orders of 2. You're then looking and saying, well, oxygen's smaller. So then O2 should be shorter than C2. So when the bond types are the same, you compare the atom sizes, the atomic radii of the atoms from chapter 7. Last question on this activity, another MO question. Which Lewis structure is most consistent for C2? Let's just try to think of how we might look at C2. 8 electrons, so 2, 4, 6, and then 8. And so then we have, these are the star. So our bond order here is going to be 6 bonding electrons minus 2 anti-bondings times half. So the bond order is equal to 2. So we have a double bond. So I would say a double bond. And then the anti-bonding electrons just kind of result in lone pairs. So the net result of a bond with an anti-bonding pair are lone pairs. So I'd say something like this makes sense for C2. And then each carbon has a 0 formal charge. And that this is better than this because we can't get to the quadruple bond from the MO diagram picture. So I'd say something like this is the most consistent picture of C2 with its MO diagram. All right, guys, that's activity 11. Again, a 2-week activity that kind of goes through the full range of chapter 9 for preparing for midterm 3. Thanks for the attention.